Hello, class. Today we're going to start our discussion of polynomial functions by doing an entry problem. This is from your textbook, but for your convenience, I have put the problems here on the smartboard. I'm going to do the first one with you. It asks for you to construct a polynomial function with the given characteristics. So I'm going to do 104 with you. So for this one, it says it has zeros at -4, -1, 2. It is a third degree function. What that means is each of the zeros will have multiplicities of 1, so there'll be no double or triple roots because there are 3 unique roots here, 1, 2, 3. So we can begin by writing y equals a, because every polynomial can have a multiplier, like an a value on the outside. And so for the first 0, -4, the corresponding factor would be x plus 4. For the next 0, -1, the factor would be x plus 1. And for the final 0, 2, my factor would be x minus 2. So each 0 corresponds with a factor. Now it says it has a y-intercept of 16. So what I'm going to do is evaluate this at the point 0, 16. So I can solve for a and then find what a would need to be given a y-intercept of 16. So I'm going to plug in 16 for y and 0 for x. Evaluating, I get a times 4 times 1 times a -2. So I get 16 equals -8a. Divide both sides by -8. I get that a equals -2. So finally, I can write my polynomial. We're going to keep it factor. That's going to keep it cleanest. So it's just -2, our a value, times x plus 4 times x plus 1 times x minus 2. Now I'm going to ask you to pause the video so that you can complete the other problems, 103, 105, and 106. And then if students could be called on to come to the board to explain their answers, that would be fantastic after everyone is given time to work. So please pause the video at this point. Okay, now we are back. Again, we're still in 5.1b discussing polynomials. And I'm going to ask the question, which could be the graph of this polynomial? It is a negatively oriented cubic polynomial with a y-intercept of -4. Okay, so I can take a look at those things. A negatively oriented cubic, because it's a cubic, the end behavior must disagree. So it either has to go from low to high, or it has to go from high to low. And you can refer to your notes from yesterday to remind yourself of this. So an odd coefficient, or an odd degree means the end behavior disagrees. So one's up and one's down. The way we determine which it is, this one would indicate a positive lead term. The way I think of it is that if it is increasing left to right, something like this, it's increasing left to right, it has a positive lead term. If it is decreasing left to right, starts high and goes low, that would indicate it has a negative lead term. Since this particular function has a negative lead term, the only option it is D. And then we can also look, the y-intercept, as I said, is -4. And here it is going through the y-axis. around -4. So that would be the only graph that could match this polynomial. When I look at analyzing the graph of a polynomial function, I feel like we're doing a little too much with all these steps. So I'm going to take out some of the steps just to simplify it, because really you can get a nice sketch of a graph without step 4 and 5. So I'm going to take those out. And then I'm going to look at the remaining steps. So step 1, and this is from your textbook, so I'm just editing it a little bit, determine the end behavior of the graph of the function. If I were to multiply these factors out, this is a squared term, a linear term, and a linear term. So we have x times x times x. Let me say that again. X squared times x times another x. If I were to multiply this out, this is going to be a degree 4 function, meaning the highest power of x will be x to the 4th. If I were to multiply it out, x times x squared times x, and then x squared times x again, my lead term would be positive x squared. So it is a degree 4 polynomial with a positive lead term coefficient. So what that ends up looking like is like that field goal person, where the degree is 4. It is an even degree, so that means the end behavior must agree. And since it is a positive lead term, these are both increasing left to right. So my function basically starts high and stays high on my graph. I might not put those on the graph right away, but I just kind of did that to show that that is what it will end up doing, is go high for the left end behavior and the right end behavior. Step 2 says find the x and y intercepts of the function. We know the x-intercepts occur when y is 0. So if I write 0 equals x squared times x plus 3 times x minus 2, I can then set each of the factors equal to 0. To solve, I get x squared equals 0. We get a double root at x equals 0 because x equals 0 twice. Double root. Then I get a single root at x equals -3, and another single root are 2 at 2. These are single roots. So I have the graph crossing the x-axis at 0, -1, 2, 3, and +1, 2. When I look at my y-intercept, we know that occurs when x is 0. So y would equal 0 squared times 0 plus 3, which is 0, times -2. So my y-intercept is 0. Okay. So recall that at 0, I have a double root. So here I'm going to have a double root. And then the other ones are just single roots. So because it's degree 4 positive lead term, I start high. I have to pass through at this point. Now I have to go through this point right here, bouncing off the x-axis. So I can't go straight through 0, 0. I have to bounce off because it's a double root. So I'm going to turn around, bounce off, and then I have to turn around again to get through this root, and then we can see I have this like W kind of shape. The things I don't know exactly. I don't know exactly how low to go. So this point right here, I don't know how low to go right there. This point right here, I don't know how low to go. So this method gets you a good sketch of the graph, but it is not a perfect graph. So it could go lower. I could go through this, go down here, go up higher. It could be a little steeper. So it could be a W like this. It could be narrower, like just little, could be steeper on all of this. Okay. calculus really helps us to answer the questions of how low do I go on these two lower points right here. So we're going to wait till we take calculus to determine those points. For now, we're getting the rest of the pieces in place. The fact that the end behavior is increasing on both ends, the fact that these are our x-intercepts and our y-intercept, and the fact that at this intercept, I'm not going through, it's 0, 0, I'm bouncing off the axis. So those are the things I'm looking for, is that you have the correct intercepts, the correct end behavior, and that you are bouncing off the graph when you need to bounce off the graph, like at a double root. Okay, we have a special kind of polynomial function called a power function. A power function is simply a monomial. So one term. So it's of the form f of x equals a times x to the nth power. And here are a bunch of examples. We have a first degree power function, second, third, fourth. The thing they will all have in common is they're all going to go through the origin. So because there's nothing being added onto the function, if x is 0 here, you get y is 0. If x is 0, y will be 0. So they're all going to go through the origin. That's something they all have in common. So these power functions are just interesting takes on polynomials that have kind of less things going on with them. They all go through the origin, and also they're not going to have as many transformations because of that. So like this is our quadratic function flipped over and then scaled by a factor of 5. So it is a vertical stretch by a factor of 5. This is our cubic function with a vertical stretch factor of 8. So they're just a vertically or horizontally, or sorry, vertically stretched parent graph. It might be flipped over. It's flipped over if these are negative. So let's take a look at these graphs. So if the function is even, the power of the function is even, you're going to get all U-shaped graphs, basically a parabola or things that look parabola-like. The reason that is if this is positive and even, you're going to have agreeing end behavior like that, that both increase to the left and to the right. The difference between a function like y equals x squared and y equals x to the fourth is highlighted in these graphs. One thing I want to point out is that all of them will go through, if it's not stretched horizontally or vertically, they'll all go through 0, 0, negative 1, 1, and 1, 1. Because if you're taking a number 0 to any power, it's still 0. So 0, 0 is a point it's going to go through. If you take negative 1 to any even power, negative 1 squared is 1. Negative 1 to the fourth is 1. Negative 1 to the eighth is 1. Likewise, 1 to any power is 1. So that's why it goes through those 3 points. Next, I want you to note the shape of the function. The higher the power goes, the following happens. Number 1, the bottom of the function gets flatter. Okay, it looks almost like a beaker or a test tube down there. It gets flatter. So that's x to the fourth there in black. This is, sorry, x squared in black. This is y equals x to the fourth in blue. So we can notice that y equals x to the fourth, this is the one in blue, has a flatter bottom. Okay, so the bottom of this function is more square-like. The other thing we can notice is that the vertical rise is steeper. It almost looks vertical. So flatter on the bottom, more vertical on the sides. Then if we compare in this other drawing x to the fourth and x to the eighth, we can see that x to the eighth, which is in blue, is even more flat on the bottom. And it's even more near vertical on the sides. So this is just a compare and contrast of our typical parabola versus something that has a much higher even power, like y equals x to the eighth. So if we go up in power and they're all even, they don't look markedly different. It's not like I couldn't have tricked you before and say, oh, they're all parabolas. But in reality, they aren't. We have a quartic, and then we have an eighth degree function, but they all look very similar. Again, the differences are the bottom of the graph and then how vertical the sides are. So that is a power function where the power is even. Here is a power function when the power is a positive odd number. So if it is a positive odd number, you know, this is third, fifth, seventh, ninth, etc., the end behavior is going to disagree, because if you have an odd degree function, the end behavior disagrees. It says it is positive, so we're saying it goes from low to high. Okay, so overall, it's increasing in that graph. I mean, it might do something super interesting in the middle, but it goes from low to high. Because if I take something to a third power, to the fifth power, to the seventh power, and let's say that thing I'm taking to the power is -1, -1 to the third is -1, -1 to the fifth is -1, -1 to the seventh is -1. So all these graphs go through -1, -1. All of them go through the origin, because 0 to any power is 0. And all of them go through 1, 1, because 1 to any power is still 1. So those are some similarities. We have the end behavior as a similarity, and it going through those points is also a similarity. The differences are kind of similar to our even graphs, where it really flattens out for longer on the x-axis. So if I'm comparing x cubed with x to the fifth, the blue one is y equals x to the fifth. If I am comparing those, x to the fifth is flatter along the x-axis for longer. Okay, so it flattens out even more on the x-axis. Additionally, the higher the power, the more steep the rise. So we have a pretty steep rise for the fifth power, and then we have a pretty steep fall. So if we think of this as like a changing slope, the slope is steeper and the slope is steeper, the higher the power. And then for this next graph, we're comparing x to the fifth and x to the ninth. Look at x to the ninth. You hang out on the x-axis for longer. I am on the x-axis for longer before I pop up. So again, more flat behavior on the x-axis. And also the rise for x to the ninth is steeper than the rise for x to the fifth. And also the fall, if we're looking in the other direction, is steeper for x to the ninth. So it's, I mean, it's not a right angle, but it's right angle-ish. It's just like a curvy right angle. The higher the power, think of x to the 20th, you know, it would look almost square-like there on the bottom. So these are just exploring what happens when we have higher powers. X squared, x to the fourth, x to the eighth, x cubed, x to the fifth, x to the ninth. What happens along the x-axis, and then what happens to the end behavior? Okay. So if we were to graph one of these higher powered functions that has some transformations on it, this is a fourth degree graph. The 2 moves it 2 to the right. The 1 moves it 1 up. Okay. So it will look very similar to a parabola, but it will have a flat flatter situation on the bottom, and it'll be a little steeper than your traditional parabola. So I'm going to go 2 to the right and 1 up. Here's my vertex. And then it's going to just be flat, and then it's going to go up. So the difference that I tried to draw there is it's flatter on the bottom, it's flatter down there, and it's steeper here. So without a discerning eye, it would be difficult to tell this from a regular parabola, but you're going to be looking, a regular parabola would be more like a U. This one has a bit more flatness on the bottom. So it's kind of a small difference, but it is a difference. If we look at the other one, we have a negative 5th degree graph moved up 3. So you take your normal, what I do is I look at the cubic graph. This is y equals x cubed. And I'm going to move it up 3. So 1, 2, 3 makes this point go up 3 on my graph. Now because it's negative, I'm flipping it over. So I go from high, I'm flattening, and then I go low. So the difference between this and the cubic graph, the transform cubic, number 1 is it should be steeper on the sides, steeper for the end behavior. Secondly, it should be flatter where you have your key point. Okay, so this part right here almost looks horizontal here. If you zoomed in, it wouldn't be horizontal, but as you draw it, it looks almost horizontal when it's at that key point. So knowing the power functions help us to know what exactly I'm transforming, and it helps me to know how it compares to the cubic graph and the quadratic graph. All right, here is your assignment. Best of luck. And notice for this, it'll say analyze the graph. I just want you to graph it.